CN. No worries. Rather than x1, x2, y1, y2. Right? So it's just a little bit of notation. Of course, I is the square root of -1. Pick one of the square roots, you call it I, right? So once you have z, you have its nemesis, z bar. I always think of this as a, you write this, and it seems to make perfect sense just to write it like this. But if you think abstractly, what did we do? Was, again, talking about this orientation. What we did was also pick an orientation by picking which root you're picking, and you can't tell the two roots apart. So abstractly, you let I be square root of -1, which is kind of abusive notation anyway, because there's two and you can't tell them apart. So you think of it as, like if you have, when I was growing up, we went to the countryside, to the cottage, like lots of people had chickens. You can't tell the chickens apart, right? So you have two chickens running around. You pick one and you want to know, this is I, so you write I on it, and the other one is -I, right? But a priori, you can't, you don't know. So everything that we do is z, we could do with z bar. There's really no difference, right? But once you pick it, you pick it. It's the same thing as picking the orientation here. Once you pick it, you want to stick with it. So z bar. Now, we also want to differentiate. Now, if I take the outer derivative, the exterior derivative of z and z bar, if I think of them as functions, I get that I get dz is dx plus I dy, because I want to think of the exterior derivative as linear, right? So I get also for the dz bar, but it's just a computation. I'm not really defining these things, right? I'm thinking of x and y as my variables here. So we have you have dz and dz bar. Now I want to differentiate functions. That's the way that we get to CR geometry. So we want to have the duals to these. So duals to dx and dy are simple. Right? You have derivative in x, and that really if duals, I'm plugging it into the one form. So if I plug this into the one form, and it's always different ways of writing. How do you evaluate a one form on a vector? So I think let me write it in the functional notation, even though it's a little weird sometimes. A lot of times you write it with brackets, but let me write it in the functional notation. So if I have, let's say, dx1, right? So if I plug in this vector into this one form, I'm supposed to get 1. If I do, let's say, dx2, plug in dx1, I'm supposed to get 0. Right? It's supposed to be the dual basis. Now, from the same, in the same way, I won't write down the general version here, but let's write down the general version for the dual basis for the DCs, and those are the Verdinger operators. So if you want to think of these as just formal operators, so we have DT is 1/2, which is a priori it seems a little arbitrary, but it's really to get that it's the dual basis of those guys. So we have J X J. I always have to think, but it has a minus sign if I write the I on top. But maybe the right way of thinking about it is that the I is on the bottom because we're differentiating with IY. And then so it's plus differentiating with respect to IY rather than differentiating with Y. Right? That's one way to remember that it should be minus here, and it's going to be the if I do the same thing for the Z bar, 1/2 plus I. That's sort of seems like kind of the opposite, right? These are conjugates of each other, right? And they have the property, they're really determined by, and you don't have to sort of think of these as, that we're defining these, we're really just taking the dual basis from here. So we have, I did forget to write down the, if I'm writing down in coordinates, right? We're thinking of each one of these as a separate coordinate, right? Or you can think of just doing all of them at once, I guess. So here I will get, if I plug in into the dvk, and again, I'll use the functional notation, completely standard, but it is a function, so might as well. If I plug in any ck, I'm supposed to get, right, the Dirac delta function, I get 1 if j is equal to k, 0 otherwise. And if I do I plug in the C bar, here, there's always going to be 0. And similarly, if I do the bar, by plugging the dk, I will get 0. Plug the bar, and the next level. All right, so that's just formal nonsense in some sense, right? We're not doing too much here, but this is really the way that we want to take derivatives. We want to think of derivatives in this way. The weird thing about this is that they look like partials, they're written like partials, but they're not partials, right? It's not, we might sometimes be able to compute them as, just plugging into some formula, taking some limit, but that's not what they are. And we'll get to this. Really, there's I in here, right? So they're not really partial derivatives in some direction. How would you think of that direction anyway, right? But one way you can think of these is the direction is like suppose that we're even in C, so n equals 1, right? So we have a plane, and so you want to think of the Z derivative. So you're taking the derivative, it's not an arrow anymore, it's a whole plane. But the whole plane has two orientations. There's the Z orientation, the Z bar orientation. So you can sort of think of it as taking the derivative this way or this way. You can think of, there's a rotation maybe. So it's, a little bit harder to think of, but so it's no longer an arrow as it would be in real geometry. All right. So now that we have this, so we have functions of x and y. This is something that I spend a lot of time trying to convince Siva that this is a good way of writing things. So if I try to keep this systematically worse. So suppose that I have some open set in Cn, and I have some smooth functions. So we're mostly not going to worry about different like ck for different k's. If something is going to be smooth, different, and essentially every function that I'm really going to worry about is going to be either smooth or analytic. So if it's just smooth is incredibly rough. Smooth is a terrible category. Even though you think infinitely differentiable is all great, it's insanely rough already. So the worst regularity that I will think of is C infinity. So suppose that I have a smooth function from U to C. So the way that I think of it well, it is a function of x and y, but you really want to think of it as a function of something interval. I'm going to write it like this: f of z bar. Even though it doesn't really make sense, right? You could sort of think of it as being defined, and we'll see this later on this set. So this is kind of a fake picture because I can't draw 4 real dimensions. But if I have C here, and maybe some other, even if n equals 1, it's 4 dimensions, 4 real dimensions, and some zeta here, right? These are complex values. I can think of this sort of diagonal, which is where zeta is z bar. So I can think of this guy being defined not in the z plane. I can think of it as being defined from some open set here, like it's related to some open set on the diagonal. And I can think of it as being defined here, and then I could write this function as a function of z bar, right? But it's not really defined anywhere else. Z bar really has to be z bar, right? Which the comment right now might not make any sense whatsoever if you're not using this, right? Of course, z bar, like the conjugate, of course, right? But most of the time, in just sort of in CR geometry, z bar doesn't have to be z bar. Z bar is going to be totally, often a totally independent variable. It's basically you're just thinking of this zeta over here as a second variable. But of course, if I have a smooth function, then this thing, for this to be defined, to have any value, the second component has to be z bar, right? But once we have this, we can think of taking these derivatives, right? And so you have the proper the way that derivatives apply here. This is really the way that you want to think about it. So the big reason for writing this, even for smooth functions, is to keep in mind how derivatives apply, right? Because we don't want to think in terms of x's and y's. We want to really think of it in terms of t and t. Okay? That's quite important for the geometry, to think in those terms, right? So, all right. So if we have a smooth function, this function of z and z bar, almost kind of independent. So what if it really was a function? It's really just a function of z. Well, then we have the holomorphic functions. So that's really the thing that we're interested in. So f, say u, and is holomorphic. So we're starting with smooth, but you start with C1 here. If it's independent of z bar, so if it satisfies these equations, basically if it's scaled by all the z bar derivatives, so if it really is just a function of f z, right? And then we'll write f z, right? And so Theo and Mayra Alan were laughing at me a few months ago, because in one of our sessions I was insisting on writing a smooth function like this, and they thought it's very much out of character for me. Because if you're composing a lot of things, writing things like this, you have to write everything twice. And so I was being way too lazy to do that. I was writing things like this. But often if I write f of z, I really mean a holomorphic function. And we'll have this notation that will have this O for oka. So that's the way that we'll write this. The regularity being and you really want to think of it as what it means is that it's oka. Yeah. Okay, like it's an interesting an interesting, you know, point. Really, like now, if you're doing research, right? So imagine that during your entire life, you wrote think 11 papers. Would you be insane famous? Probably not, right? Who writes 11 papers in their entire career and is like an extremely famous mathematician, right? Well, it could be Oka, right? Although, if you take a proportion of the Oka's papers that are readable by mere humans, it's 0 out of 11. None of those papers are readable. So if you want to read any of Oka's works, you have to read what his students wrote. There are students that would make his papers readable. But yeah, so I guess it's different times. So at those times, like nowadays, if you had 11 papers, you were trying to ask for grants, they would say, like, this guy does nothing. Don't get any grants. All right. So, and these equations are the kosher inputs. Equations. Sometimes it's the CR. And that's where we get CR geometry. Think of kosher geometry. However, CR could mean different things. So a lot of people also think CR as complex real. And if you read some old papers, it's also written as RC geometry, although nobody uses that now. And if it was RC geometry, people write it as the blackboard R and the blackboard C. So there's also another story about CR geometry that it's because it was sort of more popularized by Cohn and Rossi. Without Cohn, was it K? But it was a sort of thing that John Gangel likes to tell this story that he asked Cohn if they noticed this coincidence, and Cohn said yes, that they didn't notice that they should use it. So they could be kosher Rossi. All right, so that's CR. Now, if you want to think of smooth as smooth function that satisfies the CR equations as holomorphic functions, the easiest way to sort of think about it is always write everything as it's always best to just write out examples. The simplest examples of anything like this are polynomials, right? If I write down some polynomial, and I'm just going to write down something random. It's not going to be holomorphic, but x plus y squared minus I don't know, xy. I'm just writing down a random polynomial in x and y. One way that you could think, like, is this holomorphic? Well, yeah, you could apply. Okay, that would be annoying, right? Maybe not too bad. But one way that you could think of it, well, it's a function of z and z bar as well, right? If I write x, it's a real part. How do I write the real part of z? It's z plus z bar over 2, right? And how do I write down? By the way, here I'm in just one complex variable, but it's the same idea if I have x1, x2, z1, z2, so on, right? Same idea. And y is the imaginary part of z, so it's z minus z bar divided by y. Well, just plug that in here, right? So to have this as a function of z and z bar, if z plus b, or over 2 plus 2i times, that's going to be squared. So b minus b bar over 2i squared minus xy, so Z plus P bar over 2, and Z minus Z bar over 2I, right? And what I could do is I could expand this now, right? I'm pretty sure it's not holomorphic, but you could check this by actually expanding and making sure that not all the Z bars cancel, right? So that's the best way to think of it. And formally, like all this just gonna work for polynomials, right? Obviously, right? So it's you want to think of that's the best way to always think of it. Like it's just to think of the simplest possible examples. Just make sure that all this formal nonsense actually is makes some sense. Now, it's having polynomials, of course, not too far from where we want to go, because holomorphic functions are analytic, so that they have a power series, right? So to write power series in several variables is a little bit annoying. So people use this multi-index notation. So it's something that I will use. So if I have, instead of having just a single power, you have to power for each like Z1, Z2, and so on. So really, I have these vectors of powers, alpha 1 through alpha n. And then if I write down Z to the alpha, what I really mean is Z1 to alpha 1 times Z2 to alpha 2, again to alpha n, right? Because otherwise it would be really annoying to keep writing this, right? With this notation, I can just write down power series like this, right? And so then it just looks like a power series in one variable. Except now the alphas, like where do they vary over? Well, they really vary over maybe values n sub 0 to, and like however you write the natural numbers, including 0. You want to allow 0 in there. So if we have a holomorphic function, then we have probably all of this, right? This is one variable, right? We have analytic functions. So we have a power series, at least hopefully, theoretic functions. So having polynomials, it's fairly close to polynomials, just a special power series, right? So if we have, so this is for we'll call all functions have power series in power series hopefully. Wait. Power series representation. That's what to say. Now, this is a special power series in X and Y, really, right? So if we're going to think of, and we're going to want to think of real analytic functions, then we want to think of just power series in X and Y. Now, not every power series in X and Y can be written like this. It's like, for example, this. It's not going to be a power series in just Z, right? It's going to have, you're going to have this guy, right? So stay around. Definitely for you. Second order, I'm pretty sure that it doesn't cancel, right? So you're going to have at least a few bar. There's no way to write it like this. So if we're going to, if F is real analytic, so normally it would mean it has a power series in X and Y near every point. The way that we really want to think of it is it's a power series, but not in Z, but it's in Z and Z bar. So we're going to write it like if F is real analytic, it has a power series like it's near every point again. So now there's going to be two of these alphas and alpha and beta, alpha and beta. We're somehow summing over all of them, alpha, beta, d alpha, d bar, beta. My advisor would be angry with me for not writing beta bar. You always write. There are a lot of people write beta bar. Doesn't mean that you're barring beta. It's just that you're keeping track of there's a multi-index for the bar variables. So if you see that in a paper somewhere, it doesn't actually mean that you're barring anything. It's integers, right? When you could bar them, it doesn't do anything. All right. So you write it like that. So of course, for example, this thing is also real-algebraic. So next, now, of course, we have to think about conversions and all that. And conversions in here, if you remember from your complex analysis class, same thing in some of the variables. One variable. They have really nice conversions. You really just need to look at the largest here, at the largest qualities of product. And it's still convergence there. The largest quality that fits in here. It's actually, you get a little bit more. Any qualities that fits in there, you will get conversion. Over here, knowing how far things converge, yeah, it's not easy just from looking at you really have to look at these coefficients and compute how far it converges. So convergence for real-algebraic functions, of course, tricky. But if you somehow know where things converge, and it's always going to converge, it's supposed to have a convergence power series representation near every point, then I can plug in Z and Z bar. They really could be independent, right? I could plug in a different Z bar than Z. So I could plug in some zeta, right? Think of it as a function of Z and zeta. Of course, it would have to be. And by the way, maybe I forgot to mention on it. I'm doing all of this at the origin, of course, right? Because I'm lazy to write down like Z minus A, right? And it would be even worse here, right? So, but you get it near every point, right? So you can think of having coordinates near every point that looks like this. So we're near zero, right? And so as long as C bar is not too far away from zero, G is not too far away from zero, I can plug it random numbers here. And still get still get a function, right? So it really is, at least for real-algebraic, as long as you keep track of the conversions, which is tricky, because a lot of times the problem that you're getting in a real-algebraic function, let's say in some CN, but if you're so-called complexifying, if you're making this Z bar separate variable, it's at each point is to figure out how far can you go, and it's not so clear. It's not clear just from you can easily compute it by where the function is defined, or like even computing some integral or anything like that, like you do if you have a holomorphic function, right? So, but it is tricky, right? It's not this radius of convergence can change as you move along, and as you move towards the boundary, it can get really thin, and so it's things get very tricky, right? But as long as you're inside the domain of convergence, as long as you can take a small enough neighborhood, it's perfectly fine, and you don't have to worry. All right, so we'll talk more about that a bit later. Since we want to talk about Levi-flat, so we want to figure out what does it mean, Levi-flat, and so you have to figure out what does it mean to be pseudoconvex, and there's this we have heard pseudoconvex, but let's sort of go through these ideas. So maybe I'll start with one sort of really amazing term, and then I'll do a little bit more concrete example of this. But something that sort of tells you what's going on, and something about really convexity, right? So it's the Hardox phenomenon is a really amazing term. So suppose that I have new chart. Suppose that I have an open set. Suppose that I have a compact set K. So I did some compact subset of U. Suppose we have some topology. So let's suppose that U minus K is connected. And let's suppose that I have suppose that F is holomorphic U minus K. So the picture is I have U somewhere here. I have K. So I have I'm taking maybe making a hole in U, and F is just defined out here. And let's suppose that N has to be bigger than or equal to 2. That's important. It doesn't work in N equals 1. And we'll see. I'll prove sort of a special case of this because it's very useful to sort of think of a special case of this. And you'll see how, why that makes, where that comes in. If N is bigger than or equal to 2, then there exists capital F morphic in all of U, and little f is equal to f big F restricted to U minus K. Put it up here just to make it easier to see. So going quite a bit down here. So all right. So what does it say? So it says that I have a function here I can extend through the hole, right? Now, why do we get convexity? Well, in this hole, it could be a priori like a random, random compact subset, but it's going to have some place where it's convex. Right? So from outside, it's going to be concave, right? And so we can extend through over here it's not convex, but over here it is convex. And you can think of, well, I can extend maybe a little bit through here. So that's actually one way to prove this term, is to start extending by little bits. And everybody always thinks that's the way that this term is usually proved. It's not, because it's insanely hard to do. Because this K is the way I drew it. Yeah, sure. But the K is just a random compact set. So the hard part is, if you're going to be extending a little bit at a time, is getting a single value extension. So it was it's called Hardox term, but Hardox had a wrong proof of it. So Hardox proof would work if it was a simple simple K like this, but it wouldn't work if it was
But apart from the proof, I slight quibble because you cannot guarantee that big F restricted to U minus K will agree with little f. So let me give you an example of compact. In your picture, you take two concentric squares,
right?
Or you take an animus, and your compact is that animus. So,
but I have the U minus K is connected.
Is that?
Yeah. So, yeah. So that would be, that's basically the only sort of flying the ointment here. Otherwise, it would be like a really simple statement, right? But yeah, if you have a hole in here, then if you extend, then you wouldn't necessarily get the same extension out here. Yes. But you know, it's kind of a very simple condition, right? It's just a topological condition. But once you satisfy the topological condition, then you have this extension. But we're not really interested in like in the you know, in the most general case of it. We're really interested in the convexity aspect of it. But I find this like one of the most amazing theorems in several complex variables, right? And it really shows. I think it really shows this idea that it's really just convexity, and there's no you don't really have to have too much. Like there's really no geometry on K that's required, right? Now, all that we're gonna do is it's gonna be really nice geometry, right? So we're not gonna have weird things like this. We would have you know, maybe you know, nice hypersurface or nice manifold, you know, something that's K or boundary of K. But this is a useful thing to think about. So let's think about how you would prove the special case of this, and you could think of a technical lemma basically here, and it's a very useful lemma to think about. And I'll say it in a special case, and just you know give just an idea of how to prove it in a special case, you know, because it's the proof sort of tells you how all this works, right? So if we have Hartog's figure, and Hartog's proof this was using these ideas, but yeah, it's actually hard to do. So it wasn't really proved. Like Hartog's stated this during 19 something. Now I can't remember. 1916 or 13, something like that. Early 1900s, and it wasn't really proved until the 40s. It was Wagner proved it, and then everybody thinks that Wagner proved something different. So there's this other term that's called you know, after Wagner, like Wagner-Hartog's, but he didn't prove that. Wagner proved this. Wagner-Hartog's were proved by Martinelli. We won't worry about it. It's a stronger version of that. So like, it took maybe like 30 years to actually even realize that Hartog's proof was wrong. It was, you know, people didn't realize at first that this thing that I'm going to do doesn't quite work. It is kind of subtle, but for a simple case, it works.
So out of curiosity,
yeah.
The Wagner proof doesn't even attempt to use Hartog's method, or the Wagner proof is the one using the bar method?
No. That's the bar method is from the 50s, and it's Ehrenpreis. So that's you know, that's the most common proof of this is the bar method, and it's actually kind of nice. Like it really follows very cleanly. Whereas you know, Wagner's method is basically the same thing as Hartog's method. You know, they were both doing it slightly different. They were both basically doing essentially like a C2 proof, but they didn't really do C2. They did C cross R, and they took out and they were really thinking about harmonic functions rather than holomorphic functions. So functions are harmonic along one side of it. But they were doing this sort of idea. So what is the Hartog's figure? So let me first draw it. So suppose that we're in C2, and it's hard to draw C2. So I'll just draw just in these coordinates. I'm going to just look at the size. So I guess I was defining basic notation. I never defined this thing, right? So it's if this is just one variable. So if I have C1, the standard modulus, right? So we look at the moduli of the variables. Now I can draw a very specific Hartog's figure. Usually it's given with different parameters. I'll draw a very specific one. So I'll draw 1, 1/2, 1, and the orthodox figure is this guy, right? It's whatever's inside here. So I could think of it, let's call it H, orthodox. And so the orthodox, would be given by, we have, let's see, one half and one, two is, if I write it like this, the sort of quality is fine. So we just write it like this. So I have this. So I'm going to just assume these, and then the orthodox figure is given as C1 is bigger than this, and or is less than one week, right? So I'm thinking of this this region here. Suppose it's C2 is thinking of sort of rotating this way and rotating this way, right? So sometimes people draw it. It's called H. So sometimes people draw it another big picture of like this. You're thinking of rotating and rotating. So all right. So here, so I have this set over here. This is like this. The topologist, the unit topologist, so it's the unit disk is unit disk, right? These basic domains in C2, and this orthodox inside here. That I get an extension like this from H to the unit topologist. If is holomorphic in H, bigger piece of chalk, then there is this element that's holomorphic in polys, such that F restricted to H. If we extend, we're basically extending. So it's not a hole. It's sort of like we're filling in. You can think of this as a sort of a Pac-Man, right? It's biting something, and we're filling in what it's a bit of. And this is actually an extremely useful result. I was at this physics conference. They wanted to know. They wanted someone to give a set of lectures on several complex variables, and they're really interested in this sort of extension, right? And because this is really the way that holomorphic functions extend. You can take this and you can move it around. You can apply any holomorphic changes coordinates. So you can easily just think about just rotating and translating. And what you do is if you're thinking of a domain, you want to know if it's I'll define pseudoconvex in a little bit, but you want to know if it's pseudoconvex. You want to find a pseudoconvex domain that contains. You're going to sort of extend things out to a pseudoconvex domain. Can't always. You can sort of do it, and basically, it's always using this. This is the technique. This always works. Even though I said that it didn't work for orthodox, it does work. It's just proving that it works is hard, right? So it does work, so it is really, that's the way that you're doing it. And the physicists, for example, are really interested in actually doing this, right? right? Mathematicians are usually, yeah, I mean, yeah, I can do this theoretically, and then I can forget about it, right? But the physicists, are usually, well, here I have a specific domain, and so finding those those specific orthogonal domains that will sort of extend the functions that I'm interested in. So kind of a different different point of view. All right. So how do we prove this? How do we prove this? And it's really use a color. What we do is we put in analytic this. So we're gonna I'm gonna put maybe make a little bit more sense. Once I draw this, once I write it, I'm going to put disks of radius 3/4. There's going to be basically parameterized by the C1 variable, and the C2 is going to be fixed. And I have some disks that are completely in H, and then I can move that disk upwards, and it's going to go into this byte of this background, right? You can always think of, like you're trying to do this extension that you have this Pac-Man running around, whatever it bites out. That's the domain where all your functions extend. And so I can write down, in this case, I can write down an exact formula for big F. F P1, P2 by I integral now. For the boundary of the disk of radius 3/4, so I'll write it like this. And then I just write down the standard Cauchy formula. So Z1 should be a thing called zeta, Z2 is fixed. And then I have zeta minus Z2 equals zeta, right? And that's it. That works, right? Now, basically, if you think of those, you can draw this as purple again. Think of those disks, right? I have this, and if Z2 in modulus is bigger than 1/2, then the function wasn't defined up here, right? It's just defined out here. And I was my these are 3/4, and the outside, right? That's this boundary up here. Now, I shouldn't quite say that this is F, is only F inside here, but that's what I'm interested in. So I'll ignore the fact that it's also defined out here. I'm really just interested, that it extends through here, right? Then you can piece things together. Now, why does that work? And this is really the key thing, is that it's normally you can write this, this formula, even if the function was not defined all the way down here, right? Makes perfect sense, right? But then you're just going to get some function. It's not going to be equal to little f, right? So the reason why this works is that you have on these disks, when this is really filled in, I have a function that's holomorphic like this. It satisfies, if I have it out here, I mean, it's holomorphic in each variable separately, right? So it's, if I fix Z2, I just have a holomorphic function. And so it is nice and holomorphic everywhere. And so I do get, from the Cauchy formula, I get the reproducing property. And so it is giving me little f on these disks, right? And then it's basically just analytic continuation, which you get from analyticity. You have to prove that this is really giving you a holomorphic function, which is I guess clear in the doing the right thing. I think that Z1. I think I couldn't see the Z1. So in the Z1 variable, I'm just differentiating under the integral, right? And in the Z2 variable, well, I mean, this thing, again, differentiate under the integral. This thing is holomorphic where I'm integrating out here. So out here, on anywhere here, holomorphic in the neighborhood where I'm differentiating. So it's clearly holomorphic, right? And so once it's holomorphic and it's defined everywhere and it agrees with my function over here, it's going to agree out here as well, right? So out here, right? That's the key thing. And then again, analytic continuation, that means I have capital F everywhere, right? Now, how does this get you with this convexity? And the way that we get to convexity, sort of change perspective on convexity a little bit. So if we have, if we think of, it was another half an hour, right? So if we have, if we're thinking of convexity as a standard way of writing convexity, which is that you have, whatever you have 2 points, you have a line that's connecting and that's inside your domain. That's maybe not the, not the best way for us to think of it, but you can think of it as taking straight line segments and pushing them around. So if you draw a domain, if you want to figure out is it convex, what you could do, you could take a line segment, right? And instead of looking at one of them, you could move it, right? Move it around. And so if I get a family of these, for example, over here, let me maybe make it more pronounced, like it's really not convex here, then I can touch a point of the boundary with an inside of my line segment. That's why this thing is not convex, right? So that's the way that I want to think about convexity. So it's almost the same as the classical definition, but now I'm thinking of families of things. So we define pseudoconvexity basically the same way. We write, but instead of line segments, we use analytic disks. What are analytic disks? So an analytic disk U as just holomorphic function T on the disk with U, and it's closed if T is continuous. The boundary. So it's really, usually we think of so usually we're thinking of the function defined up to the boundary. It's holomorphic inside, continuous on the boundary. So that's basically our line segments. Draw the picture basically the same way. Our line segments are going to use these holomorphic functions, and the endpoints are now the boundaries. Okay, so we'll say that it's kind of a weird definition in this way because it's a negative definition. Yeah.
Assuming your analytic is
closed analytic is I'm not completely sure if it's completely standard how people use this terminology. You sort of use the whatever regularity up to the boundary that you need, but for this we need continuous. And sometimes people don't really care about regularity of the boundary at all. But we're always going to really be in this case, right? And sometimes people want more regularity after the boundary. Anyway. So like over here, you get like these are really nice. I like they get actually extend across the boundary. So all right. So just continuous is going to be sufficient for the definition. So basically, it's a negative definition. So it's a little bit tricky to think about it, right? So you is pseudoconvex. And maybe it's also, there's lots of different definitions of pseudoconvex. This is just one of them. Right? So it's one of these things that you can define and then prove that all these other things are equivalent to it, right? So maybe you can think of this either as a theorem or as a definition or yeah, but it's equivalent. So maybe I shouldn't say it's a definition. This would usually be a theorem. It's really more complicated, but that's really the way that you want to think of it. And so it's if you state it as a theorem, it's usually called the continuity such, right? And the continuity such is a positive version of this. It's basically saying that you don't have this sort of complexity, and it should really be called holomorphic complexity. But I just write pseudoconvex because it is proof that these things are equivalent. So we don't want to make it any more complicated. So if you so let's just say pseudoconvex if every family of yes close yes these are in here. So here I do have that Pn of our close this in the here. So that here you don't necessarily need to have. A lot of times people are thinking of continuous. You don't need, like for this you don't need it's that's the complication of like it depends on exactly what you want to prove. But for this you just need family. I guess it depends on what you want to get out of that. Right? Such that so say Tn goes to we call it T infinity. Now T infinity is going to be for some write it down. It's continuous function is going to be holomorphic in size. It might not be completely in oh. Yeah, it's fine. Make sure that forget it. Yeah. Yes.
There are two ends need
To
the dimension and the intensity. It's not even.
good. Yeah, let's make it J. Uniformly on declosure. Yeah. So I'm really thinking of it as function on this and still in the hypotheses of this if statement, right? And so this doesn't necessarily have to go to U, but I'm going to assume that that being that the boundary is in, right? So far I'm still in the if this is true, right? Then pseudoconvex, if for every family such as this, you get that the of the inside, of course, holds, right? So basically, we're precisely well, that I have a family of disks. The boundaries stay inside. So in limiting this, you're still inside your U. But the inside of the limiting disk. So this is really the feed bit, right? And these are the feed shapes, right? They uniformly approach. It's limiting this that you're not getting this. You cannot touch the inside of your. You cannot touch the boundary with the inside of your disk, right? So that's something. It's like a negative thing, right? That's what it means to be pseudoconvex, or what it's really holomorphic. It's even then it's not. That's not the definition for a holomorphic convex. It's usually you get this long, long term that has all of these things are equivalent, and they're all equivalent to being pseudoconvex. Right? So let's say pseudoconvex, right? So this is the way that you want to think about it, right? And let me just so that we get to Levi-flat, even though we're not going to talk about it too much. We have here. Just so that we have some definition. So we have, it's really about boundary of some domain. Let me write sort of a very. Let me maybe just draw a picture, because I'm going to give a more specific definition, because we're really going to want to think of smooth hypersurfaces. So let me just draw a picture. So this is going to be my M, and I want it to be because it's going to divide space into two pieces, and I have U1 and U2. We're going to say that M is Levi-flat if U1 and U2 are pseudoconvex. And so from convexity, that's really saying that we have we really have a flat hypersurface, right? And you can sort of think like what does it mean that if you're taking this, no matter how I take an interval and try to touch touch a point on a flat plane with an interval, I'm always touching with the boundaries, right? And so it's the same thing here, but now with these disks, it's a little bit, of course, these disks can sort of, they're kind of flexible, right? So maybe a priori you might it's hard to imagine why can you not always, right?
So in classical convex case, it would just be hyperplanes.
Yeah, exactly. Yeah. So exactly. So you really have flatness. So this is the this is one way of thinking of Levi-flat. It's this way doesn't really require any geometry on the boundary, but it might be a little bit harder to check, right? So what we really want to do, we want to do the CR geometry. We want to look at, suppose that we have a nice boundary, or we have a nice hypersurface M. How do we tell that that's Levi-flat? How do we tell that we cannot touch it by these analytics from either side? So that's sort of really where we are going with this. So. Sure.
So let's say you have two pseudoconvex domains,
yep.
not intersecting. And you always put the refractive surface between them.
No. So like you could have locally you could, but locally
right. You would do it C. You would take an egg-shaped thing and do something.
Yeah, but in C everything is very flat. So yeah. In C it's yeah. So in C you could do it, but I'm thinking of the question correctly. So you have two pseudoconvex domains. The global questions on this are always the hard ones. So I'm not locally yet. At least if it's sort of nice boundaries, if it's really complicated boundaries, I don't want to. I would say like I'm 90% sure that if you have smooth boundary, then locally you can do it. And we'll actually see why. But because you can make a nice change of coordinates, and you can actually make locally, if you have a pseudoconvex, a nice smooth pseudoconvex guy, you can actually make locally convex. If you have nice pseudoconvex guy, so it's actually you might need strictly pseudoconvex. I never thought about this this question, so yeah, it's it's an interesting question. Yes. So yeah, it's these things do get complicated because it is unlike in the convex and just the Euclidean case where you really just have everything flat. You can imagine things very easily, right? Whereas here there is this sort of flexibility, and it's hard to exactly tell. There is some flexibility, but for example, why can't I make like why can't that these I can put discs like this, but well, why can't I maybe like go around this hole, right? And then it's not clear. Or why can't I go like out here, right? If my discs are flexible, why can't I just bump them out somehow? And I can't, right? And maybe one way of thinking about it is you have holomorphic functions are harmonic, right? And so it's in one variable, right? And so you have there's no maximum principle, right? So you have to always sort of like if I bend in one way, then I have to bend it the other way, right? So, but it's still hard to sort of imagine how that works, right?
So that's maybe even a simple does local imply global question, but maybe this one is no. Because by your definition, it looks like for M to qualify to be Levi-flat, right? It's sort of separating U1 and U2 globally. Whereas one can imagine hypersurfaces where this.
I'm really thinking of this as local definition, yes. But yeah.
So if you have, so the thing is, would the definition of M being Levi-flat mean that given any point, if there is a neighborhood for which this picture is true,
right?
And in fact, the portion of M in that neighborhood, so you have a point on M, you have a neighborhood, and then the complement of M in this neighborhood is U1 and U2,
right?
Both are pseudoconvex. If this happens for every point, then M is Levi-flat. Is that the definition you?
Yeah, I mean it's equivalent. So yeah,
so here the going from the local implying the global does work out.
Right, but I'm thinking, but what if you have two? Like I think the question was like you have two pseudoconvex things, but they don't
Yeah, this is a separation.
Right, separation question. But like there might be lots of room to put in the Levi-flat. I would assume you can, but you know, don't really quote beyond that. But yeah.
So this is of course a simpler question because it's not a separation question. Because the way you stated it seemed like for M to qualify as Levi-flat, you have a global definition.
Right, and that's why I said like I'm going to draw a picture rather than like make it. Yes, it is. So a lot of these things about pseudoconvexity and the geometry, there is a lot of times that you do get global analogs, and those are generally the hard parts. So pseudoconvexity, you can either define it globally, and the way that I define it here is globally, but it's actually equivalent to being just local definition. So it is enough to get this, and that will sort of come up when we get to CR geometry, because that's just global, right? So then if we get this just locally, the problem, of course, if I'm doing this sort of global definition, then these disks or these line segments would be very, very long. So how do you know it doesn't work for very long segments or very large disks, right? Right, but it does work. Right? But that's always the hard part of this question. So it's in like for standard convexity, and so we'll get to the sort of the different geometry way of, or I guess, not even that fancy, but the geometry version of defining pseudoconvexity and Levi-flat and all that. It's really just looking at the derivatives. So you can do the same thing for convexity. And it's the same idea that if you have something that's locally convex just by sort of thinking of the Hessian and thinking of eigenvalues of the Hessian, to show that you have classically convex is a much harder question because that's a global definition. Like so and it's again much harder in the complex case, and that's really we're not going to talk about like the D-bar questions, right? Or exactly this sort of trying to piece local things together globally, and that's much harder here than in the classical Euclidean
I'm
case.
just using the CPM example.
Yeah.
You don't have. Maybe you could construct two things in CPM. Your pseudoconvex domains in CN could come from something in CPM, and then that would tell you that you cannot have smooth, very flat separating them because they're in CPM. Like right?
Right.
So you take two things in CPM,
and
then take out the hyperplane. You get two domains in CN. One is unbounded, one is bounded, and you cannot separate them with a Levi-flat hypersurface because that would become one in CPM, which is not possible. And so no, but I guess in dimensions higher.
Yeah.
Right? As a counter example.
It would like if in a PN, maybe you would have singularity at the end. You're just doing it in CN.
No, but I borrow domains from I borrow things from CPN.
Yes, so doing it.
Construct two pseudoconvex domains in CN.
And then try to separate it by.
And then if I could separate, I would end up getting something in CPN, which is a configuration.
Yes, so I'm hoping to get to that.
Okay, I'm not trying to give away your.
No. That's perfectly fine. So
Potentially you will like become.
Yeah, but I guess it would be sort of answering like answering in the negative, but it would like that. Answering that question would be much harder. Right? It seems. Or maybe much easier.
Depends on how she's actually proposing a counterexample.
Right. Right.
Because she's using CPM
to
be able to construct a pair of domains,
which aren't separated.
And in a sense, the way they're constructed in CPM, there is no choice but the separation.
Right.
To be something that's sitting in their common boundaries.
But it's what I'm saying is it's not quite if we're thinking in CN and not CPN,
no,
then it's not clear if it's a counterexample.
No,
you can remove the divisor and
exactly. I'm starting with
right, but you could have the but maybe there does exist. I mean, there do exist singular guys in CPN, and maybe the singularity is just at infinity.
Oh, so unless the divisor is completely contained inside one of the two, which is going to be a problem because we cannot have a divisor in pseudoconvex. So I was hoping that my divisor would be sitting intact. So when I remove it, I'm not removing any piece of the Lebl flat.
Right, yeah, but that won't work. That won't work. Yeah,
yeah,
like you're always going to hit, like the divisor is like always going to hit the right, yeah, no, so you could have the singularity, like the singularity could be fairly small. There are limits. Like,
like if you take absolutes even equal to absolutes, that is kind of a singular Lebl flat. So absolutes even equal to absolutes.
Oh, yeah. Like yeah. And that's singular at this one point. Yeah.
Sorry. Doesn't matter.
So you could have so that's why I'm saying like it could be so. If the question would be asked in CPN, then it's not true.
Yeah.
In the projective space, at least in n bigger than 3, it's something, and probably in n equals 2 as well. But who knows? But that's what like so it's like probably globally hard question, maybe even in CN, because it's impossible in projective space. We just add a few more points, right? But maybe if you add singularities, so it really depends, I guess, on what you want from your question. If you want a Levi-flat, because we're going to talk about like singular Levi-flat.
If you allow singular, then already the answer is no, because you take a singular one, and then those two cannot probably be separated by a smooth one.
Yeah. So if you want a smooth one, then the answer is probably no.
Because you take a singular one.
That's true. Yeah. So. Okay, so let's wait a bit. Maybe it's too easy.
Master's project.
Yeah, master's project. But it might be one of these. It's because it touches on probably really hard questions. So it might be one of these I think. What is it? Hardy's? Master's project, PhD project was proof the Riemann hypothesis. So it's like a simple thing, like how hard can it?
I thought even Gauss Fourier was like something else.
It could be.
Yeah.
So it's maybe it's that sort of master's project. All right. But I guess we're getting very close to the end. But so. I really didn't get it as far as I wanted. Let's 5 minutes. It's to but anyway, let me at least sort of quickly give where we're going. So we want to get to pseudoconvexity, but in a more geometric way. So we don't want to look inside the domains. We want to look on the boundary. So we want to look at derivatives. So I want to get. So let me just maybe just start with the write down the tangent spaces in a nice way. So we sort of had this already. Right? So we have d by j and d by j polar. We can of course think of these as tangent vectors at a point. Well, can we? Because they had this I in there, right? Now we can always maybe go here. And always think of the x ones as tangent vectors. They're actually nice, you can think of them as arrows, in directions. So we have there's a any point P from Cn, right? I mean, this is just, I'm thinking of this as a real manifold. So this is just the R2Ns, and so this is just the span over R of this. All the different derivatives. These guys are not there, right? But what I'm going to write, and I sort of recently sort of changed my mind on how to write this. I used to write this as a tensor, and then somebody convinced me that it's not quite right to write it as a tensor. So I'm gonna, and this seems to be more standard anyway. So I'm just gonna not write the tensor thing. It is a tensor. It is a tensor, but it's a tensor over the reals, and so you get real vector spaces. And so it's and then you have to put a complex structure on it. So it's maybe not completely correct, right?
That's the whole point of extending the spaces, right? That you get.
So it's so I'm just gonna write it like this. It's just so that we don't because it's not, we don't care about the algebra of it. So might as well not worry about the algebra. So it is a tensor and it isn't a tensor. It's a tensor with extra structure on it. So you basically do the same thing, but now you do it over C. So you complexify this vector space. And take the same basis, right? So yes, it is, you could tensor with C over the real numbers. That would be the same thing. It's just taking a basis and taking a complex span rather than taking a real span, right? And that's really the way that you just want to think about it. Like, there's no, we're analysts, so let's not worry about algebra. Right? So now this, once we're here, these guys are in there, right? So now we can write it C of also the wash. And that's really the way that we're going to think of this complexified tangent space, right? So we can do this with any manifold. Let me basically end there. I think we're right at the end. So a little bit more detail next time. But if we have a manifold M, but I mean a smooth manifold, so something that's given as a vanishing of a smooth function where the derivative is not zero, at least on M. So, not writing all the details, but next time. And so you can write down P in M. You can write down this. You can take any basis of it. Do the same thing as I did over here. Go from R to C, and you get CPM, CPM. So this is really going to be the thing that we're going to look at. And this thing nicely splits into two pieces. It splits in the Z derivatives and the Z bar derivatives. And then we can split this thing into the Z and Z bar derivatives. And then you realize that you can't. There's going to be some extra bits, and these extra bits, if you have a hypercircle, let's say, there's going to be one extra dimension. That extra dimension, that's really the thing that you want to look at. And that's the thing that's getting you where you can look at convexity. So if you have some vector fields, if I want to think about flat as think about curvature, like how do you get a curvature? You take commutators of vector fields, and basically you're trying to figure out how far you're not computing, right? It's and basically it's going to be that over here we're going to some bits that are the Z's, some bits that are the C bars, and then there's this other direction that is called the bad direction. If I'm going to start taking commutations of vector fields, I'm going to look at how much of the bad direction I get. And if I never get the bad direction, I'm going to be flat, right? So that's basically the idea. It's that I'm getting sort of a nice integrable, looking at just the C's and the C bars, I'm getting an integrable structure. That's like flat, right? That's basically, there's no curvature in the CR sense, right? So let's leave it there under right part. That's nice. Right. Hopefully it's going to go faster next time. It's slower than I wanted. I don't know, but the proper question there is to ask for a smooth line or ask.
Yeah, I think
I bet smooth is going to be hard. Like, luckily, I can get strictly at that.
yeah.
But
can you yeah, I'm saying that we
like it, but if it's actually and there's frictions to they would have to be sort of
but I'm saying that even if they're not touching, just you take a change of coordinates and make one of them. The other one would still be active around. How are you going to make it? It's not here to me that even
but if you can make, the other one might still not be.
If I can wrapping around in a really fast way, it's just the complexity of this program.
But then you can work very nice. So maybe like you can do.
So you can do simultaneously.
I don't know. Maybe simultaneously convexity work in the upper right. Right. You only need the value. Yeah, I don't know. But yeah, something anybody thought about, like I don't remember.
basically there you are
It's like even thinking like even the